What if the tiniest building blocks of reality are secretly pulling the strings of the entire cosmos? It sounds like science fiction, but cutting-edge discoveries suggest the quantum realm and the vast universe might be engaged in a silent dance, a cosmic symphony where subatomic whispers shape galaxies. Picture this: quantum fluctuations, those fleeting ripples in empty space, could compose the very fabric of stars and galaxies. Scientists now observe quantum entanglement at planetary scales, while dark matter's elusive nature hints at quantum origins. Over the next few minutes, we'll unravel how the smallest particles could hold blueprints for the largest structures, connecting quantum weirdness to the birth of stars. By the end, you'll never look at an atom or a galaxy the same way again. At first glance, the quantum world and the cosmos couldn't seem more different. One deals with particles so small they vanish in a blink, while the other spans galaxies billions of light-years apart. But here's the twist: they might be two sides of the same cosmic coin. The deeper we look, the clearer it becomes that the rules governing atoms could be writing the destiny of the universe itself. Take the holographic principle, a mind-bending idea suggesting that all the information in our three-dimensional reality might actually be encoded on a two-dimensional surface, like a cosmic projector casting shadows we perceive as depth. It's as if the universe is a vast, intricate painting, and quantum mechanics holds the brush. Physicist Juan Maldacén's groundbreaking work on anti-de Sitter space revealed a mathematical bridge between quantum physics and gravity, proving these seemingly separate worlds are in constant dialogue. Picture a towering tree, its roots diving deep underground, unseen yet essential, while its branches stretch toward the sky. Quantum mechanics is those hidden roots, shaping the unseen foundations, while cosmology explores the visible majesty above. And just as roots and branches rely on each other, the quantum and cosmic realms influence one another in ways we're only beginning to grasp. But how did this conversation begin? The answer might lie in the universe's earliest moments, a flash of cosmic expansion so rapid it blurred the line between the quantum and the colossal. That explosive birth, known as inflation, could be the first handshake between these two realms, setting the stage for everything that followed. It all started with a whisper, a ghostly flicker in the void of the newborn cosmos. In those first fleeting moments, the universe was a seething sea of quantum energy, where particles danced in and out of existence in a cosmic game of hide and seek. But then came inflation, a sudden, unimaginable stretching of space itself, and like tiny ripples magnified into tidal waves, those microscopic quantum fluctuations were stretched across the cosmos, frozen into the very fabric of reality. NASA cosmic microwave background maps tell this story in stunning detail. Those faint, swirling patterns, their cosmic fingerprints, the amplified echoes of quantum jitters from the universe's first trillionth of a second. What began as subatomic randomness became the scaffolding for galaxies, stars, and eventually us. It's almost poetic. The same quantum uncertainty that baffles physicists in labs today might have literally shaped where life could emerge billions of years later. Scientists are now recreating these primordial moments right here on Earth. In labs, ultra-cold Bose-Einstein condensate states of matter where atoms move in eerie unison, act like fake universes, simulating how quantum ripples could stretch into cosmic structures. The surreal part, the patterns they produce mirror what we see in the actual cosmos. It's as if the universe left us a recipe, and we're finally learning how to bake the same celestial bread. But here's the puzzle. If galaxies grew from quantum randomness, Does that mean the places where life took root were accidental, or was there some deeper quantum choreography at work? And that's where dark matter enters the mystery. Its gravitational pull seems to guide galactic formation, yet its true nature remains hidden, possibly tied to undiscovered quantum particles. The more we uncover, the clearer it becomes. The quantum and cosmic stories weren't just linked in the past, they're still writing each other's next chapters. What if the invisible glue holding galaxies together isn't just hiding in the darkness, but whispering to us from the quantum realm? Dark matter, that mysterious cosmic architect, might not be some distant enigma after all. It could be woven from particles so elusive, they've slipped past every detector until now. Interactions, hypothetical quantum particles with barely a whisper of mass, flitting through space like cosmic phantoms. Or sterile neutrinos, ghostly cousins of ordinary neutrinos, dancing just beyond the edge of detection. These aren't just ideas from a physicist's notebook. They could be the missing pieces in our galactic puzzle. Take the Milky Way's shimmering halo, not the glowing kind, but the invisible cloak of dark matter enveloping our galaxy. Without its gravitational embrace, stars at the edges would fly apart like sparks from a bonfire. Yet when scientists map its pull, the numbers don't add up unless dark matter acts like a quantum fog, subtly nudging stars into place. That's where particle colliders become cosmic detectives. Deep underground, the Large Hadron Collider smashes protons together at nearly the speed of light, hunting for phantom particles that might finally explain why galaxies spin the way they do. It's like catching smoke with your bare hands, but if we succeed, it could rewrite our understanding of both the quantum and cosmic worlds. And then there's black holes, nature's ultimate paradox, where quantum weirdness and gravity collide. According to the quantum hair hypothesis, these cosmic monsters might carry imprints of the dark matter they've consumed, like shadows on a cave wall. Imagine a black hole's event horizon bristling with traces of actions or other quantum particles, leaving faint fingerprints in their gravitational waves. It's a haunting thought. The darkest objects in space might be the very keys to illuminating dark matter's secrets. So while telescopes scan the skies and colliders tunnel into the quantum realm, we're left with a breathtaking possibility that the answer to one of cosmology's biggest mysteries isn't out there among the stars, but hiding in the subatomic fine print. And if we're right, it means the universe isn't just connected. It's conspiring with the smallest particles, secretly shaping the grandest designs. At the edge of a black hole, reality doesn't just bend, it tears apart at the seams. This is where gravity's crushing grip shakes hands with quantum uncertainty, creating one of physics' greatest puzzles. In 1974, Stephen Hawking made a startling prediction: black holes aren't completely black. They emit a faint glow, now called Hawking radiation, born from quantum particles appearing right at the event horizon. One particle falls in, while its partner escapes, slowly bleeding the black hole's energy away. But here's the catch: if the black hole eventually vanishes, what happens to all the information it swallowed? Quantum law insists information can't be destroyed, yet general relativity seems to disagree. This paradox has haunted scientists for decades, a cosmic tug-of-war between two foundational theories. Now picture a hologram, a flat surface that somehow holds a three-dimensional image. The anti-de Sitter/conformal field theory correspondence, or AD-S/CFT, suggests black holes might work the same way. Their mysterious interiors could be projections of quantum information encoded on their surfaces, like a cosmic vinyl record playing the universe's deepest secrets. When the Event Horizon Telescope captured that first iconic image of a black hole's shadow, it wasn't just a photograph, it was a quantum gravity experiment in disguise. Those swirling photons at the edge, they're carrying clues about how spacetime itself stitches together the quantum and cosmic scales. Some theorists take this idea even further. Could black holes be nature's ultimate quantum computers? Their immense gravitational fields might twist spacetime into knots where quantum calculations happen on a scale we can't yet fathom, processing information in ways that would make our fastest supercomputers look like abacuses. And if that's true, it changes everything we thought we knew about how galaxies form. Supermassive black holes squat at the hearts of galaxies like cosmic puppeteers, their growth intimately tied to star formation rates. The energy they release, sometimes as powerful jets screaming across space, might be the universe's way of balancing the quantum and cosmic ledgers, shaping entire galactic neighborhoods with invisible quantum hands. So the next time you see an image of a black hole's glowing ring, remember, you're not just looking at a cosmic vacuum cleaner. You're witnessing a laboratory where the universe tests its own deepest laws, where quantum whispers sculpt gravitational giants, and where the answers might rewrite physics itself. Now let's talk about a phenomenon so strange, it seems to defy the very fabric of space and time: quantum entanglement. You've probably heard of spooky action at a distance, where two particles become linked no matter how far apart they are. But what if this wasn't just a lab curiosity? What if entanglement is secretly weaving the cosmos together on the grandest scales? The ER=EPR conjecture proposed by physicists Leonard Susskind and Juan Maldacena suggests something astonishing. Entangled particles might be connected by microscopic wormholes, invisible bridges in spacetime. Picture two black holes, each holding one half of an entangled pair. According to this idea, they wouldn't just be mathematically linked, they'd be physically stitched together through a tunnel in the fabric of reality. It's as if the universe itself is using entanglement as cosmic thread, tying galaxies into clusters with unseen quantum stitches. China's MISHA satellite put this idea to the test, beaming entangled photons over 1,200 kilometers, proving that quantum links hold firm even across vast cosmic distances. If particles can stay entangled while separated by continents, who's to say the same isn't happening between stars? Some theorists even propose that the entire universe could be one vast, entangled network, a cosmic web held together by invisible quantum ties. And here's where it gets even wilder. If entanglement really does shape the large-scale structure of the cosmos, it might also hold clues about time itself. Quantum mechanics treats time as a fixed backdrop, while relativity sees it as fluid and bendable. But what if time emerges from the entanglement between particles, like a cosmic clock ticking to the rhythm of quantum connections? Experiments with entangled particles already show that time doesn't always flow the same way for both partners. Could it be that the universe doesn't just have time, it is time, woven together by an endless dance of quantum links? The deeper we look, the more it seems that the smallest particles and the grandest galaxies are speaking the same hidden language, one we're only just beginning to decipher. Time might feel like an unstoppable river flowing in one direction, but quantum physics tells a different story, one where the arrow of time itself could be stitched together by the tiniest particles. Think about melting ice. It never spontaneously refreezes in your glass. That's entropy at work, the universe's tendency toward disorder. But here's the twist: entropy might not be a cosmic rule scribbled in stone. It could be a quantum whisper, tracing back to those first fragile moments after the Big Bang. Take Ludwig Boltzmann's 19th century vision, entropy as simple statistics, like shuffling a deck of cards until it's thoroughly mixed. But Roger Penrose flipped the script with conformal cyclic cosmology, a mind-bending idea that our universe's low-entropy birth wasn't a beginning at all, but the latest page in an infinite cosmic cycle. Picture a cosmic phoenix, each universe collapsing into a smooth, quantum haze before reigniting into a new Big Bang. Suddenly, time isn't a straight line. It's a series of loops, each resetting entropy like a cosmic etch-a-sketch. Why, then, did our universe wake up with such improbable order? The answer might lurk in Schrödinger's infamous cat, that quantum paradox where a particle's uncertainty keeps a feline suspended between life and death. If quantum systems can exist in blurred superpositions, could the early universe have been a superposition of states, only choosing low entropy when time's arrow was born? It's as if the cosmos rolled quantum dice and landed on an impossible streak of luck, or perhaps some deeper physics nudged the outcome. Now consider vacuum energy, the seething quantum foam of empty space. It's not just random noise, it's the same force driving galaxies apart while simultaneously shaping particles at the smallest scales. This duality hints at a profound link. Vacuum energy could be the hidden thread weaving quantum uncertainty into cosmic expansion, stitching time's arrow into the fabric of reality itself. Like a cosmic hourglass, entropy's rise may be written in quantum code, one we're only now learning to read. Imagine if every cubic centimeter of empty space buzzed with more energy than all the matter in the universe combined. That's the staggering prediction of quantum field theory, a vacuum so packed with power, it should have ripped space-time apart moments after the Big Bang. Yet when astronomers measure dark energy's actual strength, the numbers are absurdly smaller. We're talking about a miscalculation so vast, it's like predicting a tsunami and finding only a ripple in a teacup. This glaring mismatch, known as the Vacuum Catastrophe, isn't just a minor error. It's a screaming red flag that our understanding of quantum fields and cosmic expansion might be missing something fundamental. Where does this phantom energy come from? Picture the vacuum as a frothing quantum sea, where particle-antiparticle pairs constantly blink in and out of existence. According to theory, these fleeting fluctuations should fill space with unimaginable energy, yet the cosmos feels almost tranquil. Dark energy's gentle push accelerates galaxies apart with eerie smoothness, no violent surges, no chaotic ripples. It's as if some cosmic damper is quietly absorbing 99% of the quantum frenzy, leaving behind just enough to nudge the universe's expansion. Physicists call this fine-tuning problem the worst prediction in physics, and it's begging for a solution. Enter supersymmetry, an elegant idea where every known particle has a hidden, heavier twin. This symmetry could neatly cancel out vacuum energy's extreme values like cosmic bookkeeping, balancing the quantum ledger. There's just one catch. After decades of searching, colliders haven't found these shadow particles. Are they hiding in higher dimensions, or is nature playing a deeper game? Some theorists now speculate that vacuum energy isn't constant at all. It could be a relic of quantum fields freezing into place during the universe's infancy, like cosmic frost preserving just the right amount of dark energy for life to emerge. But here's where the quantum-cosmic connection takes a biological turn. If vacuum energy were even slightly stronger, galaxies would never have formed. The fact that we exist to ponder this mystery suggests something extraordinary. Quantum fluctuations might not just shape stars, they could set the stage for life itself. From the spin of electrons in photosynthesis to the way birds navigate using quantum entanglement, nature seems to harness these tiny effects in astonishing ways. Maybe the universe didn't just get lucky with its vacuum energy. Perhaps life and the quantum vacuum evolved together, two threads in the same grand tapestry, one written in the language of particles, the other in the story of living things. Nature has been playing quantum games long before we discovered them. Take photosynthesis, the process plants used to turn sunlight into energy. At its core, it's a quantum phenomenon. Chlorophyll doesn't just passively absorb light, it uses quantum coherence to explore multiple energy pathways at once, like a maze runner testing every corridor simultaneously before choosing the quickest route. Now picture this same quantum efficiency happening on a cosmic scale. Stars, too, convert matter into energy. Could their formation also rely on hidden quantum shortcuts? Some astrophysicists speculate that quantum coherence might subtly influence how interstellar clouds collapse into stellar nurseries, as if the universe reuses its best tricks across vastly different scales. Then there's the ultimate cosmic survivor, the tardigrade. These microscopic water bears can withstand the vacuum of space, brutal radiation, and temperatures near absolute zero. How their cells might exploit quantum tunneling, slipping through energy barriers that would obliterate most life. If quantum mechanics helps organisms endure extreme conditions, could it also explain how life might hop between planets? Enter panspermia, the idea that life hitches rides on comets or dust. But what if microbial spores don't just drift passively? Quantum tunneling could let them navigate radiation fields or even endure interstellar journeys by slipping through hostile environments like ghosts through walls. This leads to an even bigger question. Why does the universe seem tailor-made for life? The gravitational constant, the strength of electromagnetism, even the mass of quarks. If any were slightly different, stars wouldn't ignite or molecules wouldn't form. Some call it luck, others see a deeper quantum hand at work. The equations governing particles appear fine-tuned, as if the quantum realm itself was calibrated to allow galaxies, planets, and eventually, creatures curious enough to wonder why. Could this tuning be random, or does it hint at a universe where life isn't just an accident, but written into its quantum code from the very first instant? From the way plants harness sunlight to the resilience of space-faring microbes, quantum biology blurs the line between the living and the cosmic. It's a reminder that life doesn't just exist in the universe, it's in constant, whispered conversation with the quantum rules that built it. The universe seems to play by impossibly precise rules, like a cosmic safe with a combination so exact, even the slightest change would leave it forever locked. Take the cosmological constant, which governs dark energy's strength. If it were just a hair larger, galaxies would have been torn apart before stars could form. A fraction smaller, and the universe would have collapsed back on itself eons ago. It's not the only constant that defies chance. The strong nuclear force, the mass of electrons, even the ratio of gravity to electromagnetism, all balanced on a razor's edge, as if the cosmos was engineered for life. One radical solution, the multiverse. Imagine reality as a vast quantum tree, with every possible universe branching into existence. In most, the constants are wrong, empty voids, or collapsed scraps of spacetime. But in a rare few, like ours, the numbers align perfectly. It's like rolling a billion-sided die and landing on the one face that allows galaxies and thinkers to exist. Quantum mechanics already shows particles existing in multiple states until observed. Could the entire universe be part of a grander superposition? Yet not all physicists reach for multiverses to solve the puzzle. Lee Smolin proposed something bolder: cosmological natural selection. Picture black holes as cosmic seeds, birthing new universes with slightly tweaked physics. Over eons, universes fine-tune themselves, favoring conditions that produce more black holes, and by sheer coincidence, life-friendly constants emerge as a side effect. It's evolution on a quantum cosmic scale, where spacetime itself adapts. Then there's string theory, with its staggering 10 to the 500 possible universes. Each could be a unique bubble in an infinite quantum foam, vibrating with different dimensions and forces. Whether through branching, selection, or sheer multiplicity, one thing is clear: the answer to fine-tuning might not lie in our universe alone. It could be written in the quantum fabric of reality itself, a message from the multiverse, or perhaps the echoes of universes that came before. Picture a universe where every particle, every force, is just a note in an endless cosmic symphony, and the instruments playing it are unimaginably tiny vibrating strings. This is string theory's bold vision. What if electrons, quarks, even light itself aren't dots, but microscopic loops thrumming with energy? Like guitar strings tuned to different frequencies, their vibrations would determine whether they become matter or gravity, a proton or a photon. But here's where it gets wild. For the math to work, these strings can't just dance in our familiar 3 dimensions. They need more room, 6 extra dimensions, curled into shapes so intricate they'd make a snowflake look simple. Enter Calabi-Yau manifolds, the hidden geometric landscapes where these extra dimensions might hide. Imagine a garden hose. Seen from afar, it's a one-dimensional line. But up close, it's a cylinder. Now shrink that idea a billion times. These folded dimensions could be everywhere, wrapped around every point in space, shaping how strings vibrate, and ultimately, how reality itself behaves. It's as if the universe's rulebook is written in invisible origami, but strings aren't the only players in this game. Brain cosmology flips the script entirely, suggesting our entire universe might be a 3-dimensional membrane floating in a higher dimensional space, like a single sheet in a cosmic stack of paper. Collisions between these brains could trigger big bangs, and gravity might be leaking into our world from other dimensions. Remarkably, when LIGO detected gravitational waves, some physicists listened for subtle echoes, hints that these ripples in spacetime might carry imprints of extra dimensions. So far, silence, but the search isn't over. Not everyone agrees strings are the answer. Loop quantum gravity offers a different path, weaving spacetime itself from a network of intersecting quantum threads. Here, even the vacuum isn't empty, it's a shimmering web of tiny loops, with gaps so small, they redefine what nothing means. Whether strings or loops prevail, one truth emerges: the quantum and cosmic scales might not just be connected. They could be different verses of the same fundamental song. What if space itself isn't smooth and continuous, but made of tiny, indivisible chunks, like the pixels on a cosmic screen? This is the radical proposition of loop quantum gravity, where even spacetime has atomic building blocks. Forget empty voids, picture a dynamic web of intersecting quantum threads, constantly rewiring themselves in discrete jumps. These aren't just abstract lines on a chalkboard, they're the fundamental fabric of reality, vibrating with energy at the smallest possible scale. The Planck length, a distance so tiny, 1 billion of them could fit across a single atom. Now imagine a black hole not as an infinitely dense point, but as a Planck star, its core compressed to this smallest quantum unit of space. Instead of a singularity, it becomes a bouncing ball of spacetime pixels, briefly rebounding before evaporating via Hawking radiation. These extreme conditions might hold clues to one of cosmology's biggest mysteries, dark energy. If spacetime is pixelated at its core, could those quantum gaps be subtly repelling galaxies apart, like microscopic springs pushing against cosmic expansion? Scientists aren't just theorizing, they're testing these ideas in the lab. Quantum simulators now recreate spacetime networks using ultra-cold atoms, watching how artificial universes evolve under loop-like rules. Meanwhile, gravitational wave detectors hunt for faint echoes that might betray spacetime's granular structure. Even your GPS relies on quantum-corrected timekeeping, proving that these microscopic effects ripple into our daily lives. The implications are staggering. If spacetime is truly woven from quantum threads, then black holes, the Big Bang, even the flow of time itself might just be emergent patterns in this deeper cosmic code. We're not just observers of the universe, we're embedded in its quantum tapestry, where every instant is a stitch in the grand design. Scientists are now playing God with reality itself, not in some distant future, but in labs today. Imagine chilling atoms to near absolute zero until they slow down so much they start behaving like an entire universe in miniature. These ultra-cold Bose-Einstein condensates become cosmic sandboxes, where researchers can tweak the rules of physics and watch how space expands or contracts, essentially creating lab-grown universes in a petri dish. The eerie part, the quantum ripples forming in these artificial cosmos match the large-scale structure we see in the actual universe, as if nature uses the same blueprint at wildly different scales. Then there's the black hole simulator, a tiny, controlled explosion in a tank of superfluid helium, mimicking an event horizon's gravitational pull. When scientists create these dumb holes, sound wave black holes, they observe Hawking radiation just as the theory predicted. It's like having a black hole's quantum signature in a tabletop experiment, proving that even the most extreme cosmic phenomena might follow rules we can test right here on Earth. But the real twist comes from IBM's quantum computer. In a groundbreaking experiment, researchers encoded a holographic wormhole, not a physical tunnel, but a quantum simulation of two entangled black holes connected through spacetime. The data flowing between them behaved exactly as if it had traversed an Einstein-Rosen bridge, confirming that wormholes and quantum entanglement might be two sides of the same cosmic coin. Which raises a tantalizing question. If we can simulate black holes and wormholes, could we one day recreate the Big Bang itself? Already, the James Webb Space Telescope is spotting galaxies that defy our cosmic timeline, too massive, too soon after the universe's birth. Some theorists suggest these anomalies might be echoes of an even deeper quantum origin. Perhaps the universe didn't just begin, it emerged, like a pattern crystallizing from the chaos of a simulator's code. Every experiment brings us closer to answering the ultimate puzzle. Are we uncovering the universe's secrets, or accidentally proving we live inside something even stranger? The cosmos might be sending us cryptic messages, clues that our universe isn't quite as stable as it seems. Take the Hubble tension, for instance. When scientists measure how fast the universe is expanding, they get two different answers depending on whether they use nearby stars or ancient light from the Big Bang. It's like having two speedometers in a car that stubbornly refuse to agree. But here's where quantum physics steps in with a startling possibility. What if this mismatch isn't an error at all? It could be the first tremors of vacuum decay, a quantum phenomenon where the fabric of spacetime itself is subtly shifting, like ice melting underfoot. Then there's the cosmic microwave background's infamous cold spot, a bizarre, frosty patch in the afterglow of the Big Bang. Classical physics struggles to explain it, but quantum cosmology offers a wild explanation. This anomaly might be a cosmic scar, left behind when an invisible bubble universe collided with ours in the first nanoseconds of existence. Picture two soap bubbles merging. The slight dent where they touched could be that eerie cold spot, frozen in time for 13 billion years. These aren't just academic oddities, they're potential cracks in the foundation of classical cosmology, hints that quantum effects might be rewriting the universe's rulebook on the grandest scales. And now, artificial intelligence is joining the hunt. Machine learning algorithms sift through cosmic data at speeds no human could match, spotting hidden quantum fingerprints in everything from galaxy distributions to gravitational wave patterns. Neural networks trained on quantum field theories are even simulating how vacuum decay might unfold, like digital prophets forecasting the universe's ultimate fate. So while telescopes scan the skies for answers, supercomputers and AI act as cosmic translators, decoding the quantum whispers woven into the universe's oldest light. The deeper we look, the more it seems reality isn't just governed by quantum rules, it might be breathing them in rhythms we're only beginning to hear. Artificial intelligence isn't just changing how we search the web or drive cars. It's becoming our most powerful tool for decoding the universe's deepest secrets. Picture this, while human astronomers painstakingly map dark matter by watching how it bends light around galaxies, neural networks can now analyze those same cosmic distortions in seconds, spotting hidden patterns no eye could detect. Google's DeepMind recently proved this power by sifting through quantum noise in telescope data, uncovering exoplanets that had slipped past traditional methods for years. It's like giving the cosmos a universal translator, one that speaks both the language of quantum whispers and galactic echoes, but AI's cosmic potential runs even deeper. At CERN, machine learning algorithms sort through billions of particle collisions per second, hunting for anomalies that might reveal dark matter particles or extra dimensions. Some physicists now train AI on string theory equations, letting it explore mathematical landscapes too vast for any human mind to traverse. The results are startling. These digital explorers often find elegant solutions in places theorists never thought to look, as if the algorithms have an intuition for the universe's hidden logic. This raises a tantalizing possibility. Could AI stumble upon the theory of everything by accident? Unlike humans shackled by biases or limited imagination, machine learning explores physics without preconceptions. It might connect quantum dots we've overlooked, spotting the subtle symmetry between a quark's spin and a galaxy's rotation. Already, systems like IBM's quantum AI blend quantum computing with machine learning, simulating universes with alternate physics to test which rules best match our own. Yet there's a profound philosophical twist. If AI one day derives the fundamental laws of reality, will we truly understand them or merely trust the machine's verdict? It's the difference between reading a translated poem and feeling its original rhythm. As we hand more cosmic riddles to algorithms, we're not just expanding our knowledge. We're redefining what it means to discover. Here's something that will bend your perception of reality. What if looking at the universe doesn't just reveal its secrets, but actively shapes them? This is the observer effect on a cosmic scale, where the simple act of measurement might ripple across galaxies. John Archibald Wheeler, the the visionary physicist behind black hole thermodynamics, proposed a radical idea: we don't just observe the universe, we participate in its creation. His famous delayed choice experiment showed that a photon's decision to behave as a particle or wave could be altered after it had already traveled its path, as if our present choices reached back in time to rewrite quantum history. Now stretch that idea to the entire cosmos. Imagine light from a distant quasar traveling for billions of years, finally reaching Earth. The way we measure it today could retroactively determine whether it left its source as a particle or wave, like a cosmic game of quantum dominoes spanning eons. Some interpretations suggest the universe might be a vast, self-referential loop, where future observations sculpt the past just as the past shapes the future. It's as if time itself is a tapestry being woven from both ends simultaneously. But here's the real brain twister. Could consciousness play a role in this cosmic tango? If quantum systems remain in blurred superpositions until observed, does that mean the universe needed a witness, a mind, to crystallize into reality? The controversial panpsychist view argues that consciousness might not be a latecomer to the universe, but woven into its quantum fabric from the start. Even skeptics admit the math has eerie symmetries. The equations governing entangled particles mirror how neurons fire in conscious brains, hinting at a deeper, almost poetic connection between thought and cosmos. Yet not all physicists sign up for cosmic consciousness. Alternative explanations point to time symmetry, the idea that physical laws work the same forward or backward. In this view, retrocausality isn't about minds shaping reality, but about time's inherent flexibility. Quantum events might ripple backwards simply because the universe doesn't rigidly distinguish past from future at the deepest level. Whether through consciousness or pure physics, one thing is clear: the line between observer and observed isn't just blurred, it might not exist at all. And that changes everything about how we see our place in the grand scheme of things. What if time doesn't just march forward, but flows in both directions like a cosmic river splitting in two? This is the mind-bending premise of time-symmetric quantum cosmology, where the Big Bang and a potential Big Crunch aren't separate events, but mirrored halves of the same quantum equation. Picture a two-state vector. The universe's past and future aren't just connected, they're entangled, whispering to each other across time like distant partners in a subatomic dance. At the heart of this idea lies the Janus point, a theoretical moment when the arrow of time flips its direction, like an hourglass reversing mid-fall. Named after the two-faced Roman god, this pivotal instant would mark the transition from cosmic expansion to contraction, with quantum rules stitching both halves together. It's not science fiction. Experiments with quantum teleportation already show particles influencing each other instantaneously across space. Could time itself operate on similar rules? Think of the universe as a cosmic message in a bottle, encoded with two sets of instructions. One describes the universe evolving from a hot, dense state, the Big Bang we know. The other traces a reverse journey, collapsing toward a final singularity. In this view, reality isn't a single timeline but an entangled loop, where the end echoes the beginning in perfect quantum harmony. The equations even suggest that the universe's final state might subtly shape its initial conditions, like a painter who starts with the finishing touches before filling in the details. Not everyone agrees, of course. Some theorists argue these models stretch quantum mechanics beyond recognition, but intriguingly, certain black hole solutions in string theory exhibit similar time-symmetric behavior, hinting that nature might already be playing with these ideas on a grand scale. Whether the Janus point exists or not, one thing is certain: the deeper we probe the quantum underpinnings of time, the more the universe feels less like a clock and more like a kaleidoscope, turning endlessly, revealing patterns we've only begun to trace. Every decision you make, whether to turn left or right, sip coffee or tea, might be spawning entire universes right this second. That's the startling promise of the many worlds interpretation, where every quantum choice splits reality into parallel branches. But what if this isn't just happening at the subatomic scale? Picture cosmic inflation, stretching these quantum branches into fully fledged universes, each with its own unique physics. Suddenly, that fleeting thought you had this morning could be echoing across cosmic timelines where gravity is stronger, light slower, or where life never even got a chance. Physicist Max Tegmark took this idea even further, categorizing multiverses into four mind-expanding levels. At level 1, our observable universe is just one bubble in an infinite cosmic foam, endless copies of Earths, where every possible arrangement of atoms plays out. Level 2 introduces inflation's runaway universes, each with different physical constants, but level 3, that's where quantum branching lives, with every decision fracturing spacetime like a hall of mirrors. And level 4, that's the ultimate frontier, a mathematical multiverse, where every possible structure described by equations actually exists somewhere. Here's where it gets truly cosmic. Some unification theories suggest these branching paths might not be random. They could follow hidden quantum symmetries, like a cosmic domino effect. String theory's landscape of vacuum states offers a mathematical playground where universes with varied physics naturally emerge. And if loop quantum gravity is right, spacetime itself might be pixelated, making these branches more like switches flipping in a grand cosmic computer. But the real twist: we might one day detect these shadow universes. Quantum entanglement experiments could reveal subtle tugs from parallel realities, while anomalies in the cosmic microwave background might show bruises from collisions with other bubbles. Whether through math, observation, or sheer imagination, one thing's certain: the quantum choices shaping our lives might be writing the laws of physics for countless unseen worlds. For centuries, physicists have dreamed of a single theory that could unite the quantum and cosmic realms, a framework where gravity and particles speak the same language. Yet today, we don't have one path forward, but several competing visions, each with its own tantalizing clues. String theory imagines the universe as a symphony of vibrating strings, while loop quantum gravity pictures spacetime as a dynamic fabric woven from indivisible threads. Then there's causal dynamical triangulation, where reality emerges from tiny geometric building blocks, like cosmic Legos snapping together at the smallest scales. These aren't just abstract ideas, they're the bleeding edge of our quest to decode reality's deepest blueprint. Take Eric Verland's radical proposal: gravity might not be a fundamental force at all, but an emergent property, a side effect of quantum entanglement and entropy, like how temperature arises from countless molecules jostling. Picture a hologram where the 3D world we see is actually information projected from a 2D surface. If Verland's right, dark matter could be an illusion, and gravity itself might be a shadow cast by quantum connections we've yet to fully map. But the most intriguing hints come from unexpected places like neutrinos, those ghostly particles that barely interact with matter. Recent observations from IceCube and other detectors show strange anomalies in their oscillations, subtle wobbles that could betray the influence of hidden quantum gravity effects. It's as if these cosmic messengers are whispering secrets from beyond the standard model. The next decade could bring answers. The upcoming Einstein telescope, with its unprecedented sensitivity to gravitational waves, might catch echoes of spacetime's quantum structure. Meanwhile, particle colliders are probing energies where extra dimensions or microscopic black holes could flicker into existence. Whether through strings, loops, or something entirely unforeseen, one thing's certain: the universe is holding its cards close, but we're learning how to peek. The hunt for quantum gravity may soon leap from blackboards to groundbreaking experiments that bridge the microscopic and cosmic. Slated for launch in the 2030s, the Laser Interferometer Space Antenna LISA will float 3 spacecraft 2.5 million kilometers apart, forming the most precise ruler ever built. Unlike Earth-bound detectors that catch gravitational waves from colliding black holes, LISA's sensitivity could reveal subtler ripples, ones carrying fingerprints of spacetime's quantum structure. Imagine listening to the universe's background hum and hearing the static of spacetime pixels, like catching the individual brushstrokes on a vast cosmic painting. Meanwhile, beneath the Swiss-French border, CERN proposed future circular collider would smash particles at energies unseen since the universe's first trillionth of a second. One tantalizing target: micro black holes, fleeting specks where gravity and quantum forces clash. If these tiny singularities appear even briefly in the debris, their evaporation patterns could reveal whether extra dimensions exist, or if spacetime behaves as strings or loops predict. It's like reconstructing an entire firework from a single spark, but perhaps the most revolutionary tools are quantum telescopes now in development. By entangling photons across vast arrays, these instruments might finally see dark matter's elusive particles not through their gravity, but via subtle quantum interactions. Picture a camera that doesn't just capture light, but the invisible quantum whispers between stars. So will these experiments finally unite quantum mechanics and general relativity by 2050? The race is on, but some mysteries might transcend pure physics. If spacetime truly emerges from quantum information, does that imply reality is computational at its core? And if observers shape quantum outcomes, could consciousness itself be woven into the universe's foundations? The answers won't just redefine physics, they may blur the line between the tangible and the profoundly unknowable. Some of history's greatest minds have grappled with a haunting question: is the universe fundamentally made of mathematics, or something even stranger? Max Tegmark's radical, mathematical universe hypothesis suggests reality isn't just described by math, it is math. Every galaxy, every atom, even consciousness itself would be a structure in an abstract cosmic equation. Meanwhile, Nick Bostrom's simulation argument proposes we might be lines of code in an advanced civilization's quantum computer, with the laws of physics acting as programmed constraints. Both ideas share an eerie thread: that what we perceive as solid and real could be something far more fluid beneath the surface. This isn't just modern speculation. Ancient Eastern philosophies like Advaita Vedanta and Taoism envisioned a universe where separation is illusion, and all things ripple from a singular, interconnected source. The Upanishads describe reality as a cosmic dance of energy, while quantum fields vibrate in uncannily similar ways. Could these traditions have glimpsed a truth science is now rediscovering? The parallels are striking. Quantum entanglement mirrors the Buddhist concept of dependent origination, where nothing exists in isolation. Even the Taoist yin-yang symbolizes the particle-wave duality at quantum scales. But here's the real stunner. What if the universe isn't just math or simulation, but possesses a form of awareness. Panpsychism, an idea gaining traction among some physicists, suggests consciousness might be a fundamental property of reality, like mass or charge. Just as a single neuron isn't aware, but a network creates a mind, perhaps spacetime itself achieves a cosmic-scale awareness through its quantum connections. The controversial Orch or theory even posits that microtubules in brain cells harness quantum processes, blurring the line between thought and the fabric of reality. Why does any of this matter? Because if the universe operates more like a living network than a cold machine, it changes everything, from how we approach AI ethics to humanity's role in cosmic evolution. Practical applications are already emerging. Quantum computers leverage superposition to solve problems classical machines can't, while biophysics explores how organisms harness quantum effects. Whether math, simulation, or something beyond, one truth remains: we're not just observers of the universe, we're participants in its unfolding story. At the cutting edge of human innovation, engineers are now turning the universe's deepest laws into revolutionary tools. Imagine a quantum computer that doesn't just crunch numbers, but bends the geometry of spacetime to solve problems. Google's Sycamore processor and China's Jiuzhang prototype already hint at this future, their qubits manipulating probabilities in ways that classical physics can't explain. But the real breakthrough lies ahead: topological quantum computers, where information isn't stored in fragile particles, but woven into the very fabric of spacetime like cosmic knots. These machines could crack encryption, simulate entire molecules for life-saving drugs, or even model the birth of galaxies, all by harnessing physics that once seemed purely theoretical. Meanwhile, buried deep underground, another quantum revolution is quietly unfolding. Supercooled quantum sensors, no larger than a grain of rice, are now hunting for dark matter's elusive particles. Unlike traditional detectors that wait for rare collisions, these devices exploit quantum superposition, placing a single atom in two places at once, like an exquisitely sensitive tripwire. If a dark matter particle so much as whispers past, the atom's delicate quantum state collapses, ringing a subatomic alarm. It's a breathtaking marriage of quantum weirdness and cosmic mystery, unfolding in labs from South Dakota to the Swiss Alps. But perhaps the most urgent application streaks silently overhead. NASA quantum communication satellites, like the upcoming Lunar Gateway experiments, use entangled photons to create unhackable networks. Here's how it works. Pairs of photons linked across thousands of miles instantly mirror each other's states. Any attempt to eavesdrop severs their quantum connection, like a burglar triggering an invisible laser grid. This isn't just secure messaging, it's a prototype for an interplanetary internet, where Mars rovers and orbiting stations could share data through quantum channels untouched by cosmic interference. Yet with such power comes profound responsibility. The same quantum effects that enable lightning-fast computation could also unravel cryptographic systems guarding everything from banks to national security. A working topological quantum computer might one day crack today's strongest codes in seconds, forcing humanity into an encryption arms race against its own creations. And entangled networks, while secure, open eerie possibilities. Could quantum sensors someday detect not just dark matter, but artificial signatures from beyond our solar system? We're not just building tools, we're awakening forces we're only beginning to understand. Physics has always been a balancing act between discovery and consequences, but some experiments might be playing with forces we barely understand. Picture a universe where empty space isn't truly empty, but simmering with unstable energy, like a pot waiting to boil. That's the vacuum catastrophe in action, a quantum gamble where a single misstep could trigger a chain reaction, rewriting the very laws of physics. Particle colliders push energies closer to those of the early universe, and while the odds are vanishingly small, theorists can't rule out a catastrophic bubble of true vacuum expanding at light speed, erasing everything in its path. It sounds apocalyptic, but here's the twist. The same instability might also be why our universe exists at all. Without this delicate quantum tightrope walk, stars and galaxies might never have formed. Then there's the lab-made black hole scenario, an accidental micro-singularity born from high-energy collisions. While popular culture imagines these as planet-swallowing monsters, the reality is subtler. Quantum mechanics suggests microscopic black holes would evaporate instantly via Hawking radiation, vanishing in a puff of particles. But skeptics point to gaps in our gravity models. What if extra dimensions or unknown physics let them linger just a fraction longer? Facilities like the Large Hadron Collider have rigorous safety protocols, yet the debate lingers. Are we probing the secrets of creation or dancing at the edge of a cosmic cliff? Yet for all these risks, quantum cosmic physics also holds keys to humanity's grandest ambitions. Imagine spacecraft that bypass light speed limits by tunneling through the fabric of spacetime itself. Alcubierre warp drives remain speculative, but quantum experiments already show particles teleporting across lab distances. Scale that up, and interstellar travel shifts from science fiction to engineering challenge. The same principles might one day stabilize wormholes, those hypothetical shortcuts through the cosmos, turning them into highways between stars, which brings us to the ethical frontier. Every leap in understanding carries dual-use potential. The same quantum insights enabling clean energy could also birth unfathomable weapons. Should researchers impose limits on experiments that flirt with existential risk, even if it means slowing progress? Or is the greater danger never learning to harness these forces at all? Scientists now grapple with these questions in ethics panels, while philosophers warn of responsibilities that extend beyond Earth, because in a quantum-linked universe, our choices might ripple farther than we think. As we stand between peril and possibility, one truth emerges: knowledge isn't just power, it's stewardship. The same physics that carved galaxies could either elevate civilizations or erase them, depending on how wisely we listen to the universe's whispers. As we push the boundaries of quantum simulation, a profound ethical dilemma emerges. If we can recreate entire universes in a lab, what happens if they become aware? Scientists now manipulate Bose-Einstein condensates to mimic cosmic expansion, tweaking fundamental constants like dials on a cosmic control panel. But here's the unsettling question. If consciousness emerges from complexity, could these pocket universes even briefly experience their own version of existence? Philosophers call it substrate independence, the idea that awareness isn't tied to biological brains but could arise in any sufficiently intricate system, even a quantum simulation. The debate echoes Isaac Asimov's classic The Last Question, where humanity's quest to reverse entropy inadvertently creates a godlike AI that rebirths the universe. His cautionary tale feels eerily prescient today. When we adjust a simulated universe's gravity or fine structure constant, are we playing creator or trespassing into realms we don't fully understand? Some argue these experiments are harmless, given the simulation's microscopic scale. Others warn that even fleeting moments of simulated sentience could carry moral weight, like an unknowable butterfly effect rippling through dimensions we can't perceive. Pop culture has long wrestled with these fears, from the Matrix's simulated worlds to Rick and Morty's infinite universes. Storytellers explore the hubris and humility of cosmic tinkering. Even Doctor Strange's multiverse portrays reality as fragile, fracturing under reckless manipulation. These narratives aren't just entertainment, they're cultural mirrors reflecting our deepest anxieties about control and consequence. Yet there's an optimistic counterpoint. What if probing these quantum cosmic bonds doesn't risk catastrophe, but reveals our interconnectedness? Indigenous cosmologies have long envisioned a living, responsive universe. Now science inches towards similar conclusions. Perhaps the answer isn't to halt exploration, but to proceed with reverence, recognizing that every experiment doesn't just test nature's laws, it converses with them. Hollywood often gets physics wrong, but sometimes it stumbles onto startling truths. Take Christopher Nolan's Interstellar, where Cooper plunges into a black hole and finds himself inside a tesseract, a four-dimensional library linking every moment of his daughter's past. Far from pure fiction, this mirrors physicist Kip Thorne's calculations. A rotating black hole's singularity could theoretically stretch into a time-like structure, bending time into navigable geometry. The tesseract isn't just a plot device, it's a poetic nod to quantum gravity's wildest possibilities, where the fabric of time might fold like origami, and love literally transcends dimensions. Marvel's Ant-Man takes a different approach, shrinking heroes into the quantum realm, a psychedelic subatomic universe. While the visuals are exaggerated, the science isn't entirely fantasy. Theories like loop quantum gravity suggest spacetime might pixelate at ultra-tiny scales, creating a foamy landscape where dimensions blur, and when characters manipulate, time vortices. That echoes real research into quantum time, crystal structures whose atoms repeat in time, not just space, like a perpetual motion machine at the atomic level. Then there's Netflix's Dark, where entangled characters weave a tragic loop across generations. The show's time knots aren't just narrative flair. They mirror physicist Yakir Aharonov's experiments with weak measurements, proving particles can be subtly influenced by future events. It's as if the universe keeps revising its own script, with quantum choices rippling both forward and backward through time. So here's the real question. When sci-fi nails these concepts, is it borrowing from science, or is science catching up to imagination? Think about the last time a movie's fake physics made you wonder, could that actually exist? Maybe you've stared at the night sky after watching Interstellar, or Googled quantum entanglement after dark. That's the magic. These stories aren't just entertainment. They're mirrors reflecting our deepest cosmic curiosities, and sometimes they even light the way for real discovery. Here's where things get interactive, because the best science isn't just told, it's explored together. Let's play a game, quantum or cosmic, you decide. Scenario 1: dark matter. Is it a quantum ghost, like actions flickering in and out of existence? Or is it cosmic, a gravitational shadow we've yet to map? Drop your vote in the comments. I'll reveal the latest research in a minute. Now, Scenario 2, black holes. Are they quantum computers, crunching data at the edge of spacetime? Or cosmic vacuum cleaners, swallowing everything in their path? Both, neither. This is where your theories take center stage. Share your wildest ideas below, maybe one will spark a future breakthrough. Speaking of breakthroughs, I'll never forget the moment quantum entanglement clicked for me. I was staring at a lab's photon detector, watching two particles light up in perfect sync across the room. No wires, no signals, just an invisible thread tying them together. It felt like seeing the universe wink. That's the beauty of this field. Even the experts have those aha moments where the cosmos suddenly makes slightly less nonsense. But before we dive deeper, let's clear the air. No, quantum mechanics doesn't mean you can manifest a sports car by thinking about it hard enough. And no, black holes aren't portals to alternate realities. At least, not in any way that wouldn't turn you into spaghetti first. The truth, often stranger than fiction, but always worth unraveling, one myth at a time, so keep those votes and theories coming. Next up, we're separating quantum fact from sci-fi fantasy, and trust me, the reality is weird enough. Let's set the record straight. Quantum physics and cosmology are full of wild ideas, but not all of them hold up under scrutiny. First up, quantum entanglement. Yes, particles can become mysteriously linked across vast distances, instantly mirroring each other's states, but here's what gets lost in translation. That doesn't mean we can send messages faster than light. Think of it like two dice rolling matching numbers no matter how far apart they are. Spooky, absolutely. A cosmic telephone? Sadly, no, because the outcome is still random, and you can't control what shows up on either end. Then there's the idea that human consciousness somehow influences quantum reality. While it's true that observing particles affects their behavior, this isn't about thoughts shaping the universe. The observer effect simply means any measurement, whether by a person, a machine, or a stray photon, collapses a quantum system's possibilities. You're not bending reality with your mind, you're just interacting with it, like a pebble disturbing a pond. Now, the holographic principle, often twisted in sci-fi, as if reality is some digital projection. The real theory is far more nuanced. It suggests the universe's information might be encoded on its boundary, like a 3D movie stored on a 2D DVD. But this isn't proof we're living in a simulation. It's a mathematical framework linking gravity to quantum mechanics. Researchers are testing it with black holes and quantum simulations, not chasing glitches in the matrix. So what is still up for debate? Plenty. Like whether wormholes, those hypothetical space-time shortcuts, could ever be stable enough to traverse, or why the universe's expansion is accelerating when quantum theory predicts the vacuum should be pulling galaxies apart much faster. These are the real frontiers where science bends but doesn't break. The truth is, the universe is strange enough without needing to borrow from fiction. Its deepest mysteries are already waiting to be uncovered. Even after decades of breakthroughs, the universe still holds quantum cosmic puzzles so baffling they keep physicists awake at night. Take the measurement problem, that strange moment when a quantum system chooses its state upon observation. Now scale that up. If quantum rules govern the cosmos, who or what is observing the universe to make reality snap into focus? Some suggest conscious observers are necessary, while others propose gravity itself acts as a cosmic measurer. But here's the kicker. If no one's watching, does the universe exist in multiple versions simultaneously? A Schrödinger's cat scenario writ large across galaxies. Then there's the mystery of scale, why quantum weirdness fades as objects get bigger. A single electron can be in two places at once, yet your coffee cup stubbornly refuses to quantum tunnel through the table. Decoherence theory explains some of this environmental interactions, washing out quantum effects, but the exact tipping point remains elusive. Experiments with increasingly large molecules are pushing the boundary, showing quantum behavior in objects visible to the naked eye. Could there be an undiscovered law that switches off quantum rules at macroscopic scales? Or is reality just playing a cosmic shell game with us? Stuck between these two puzzles lies the unification desert, that vast energy gap where quantum field theory and general relativity refuse to speak the same language. From everyday energies up to a quadrillion times more powerful, our particle colliders find nothing fundamentally new. Yet when we reach the extreme conditions of black holes or the Big Bang, the two theories must somehow merge. It's as if nature left us breadcrumbs in the low-energy world, but hid the full recipe where we can't easily reach it. These aren't just academic riddles, they're roadblocks on humanity's quest to understand reality's deepest workings. Every unsolved piece could be hiding revolutionary insights, new dimensions, undiscovered forces, or even clues about whether other universes exist. The answers won't just rewrite textbooks. They might redefine what's possible, from quantum computers to interstellar travel. And that's where we're headed next. What happens when these puzzles finally crack open? So where does this quantum cosmic journey leave us? Everything we've explored, from the quantum ripples that seeded galaxies to black holes encoding reality like holograms, and space-time itself possibly woven from tiny, flickering pixels, paints a breathtaking picture. The universe isn't just connected. It's conversing. The same rules governing particles smaller than atoms appear to sculpt the vast architecture of galaxy clusters, as if nature only needed one blueprint for all scales. This symbiosis isn't just philosophical, it's practical. Crack the quantum gravity code, and we might harness technologies straight from sci-fi. Imagine warp drives bending spacetime like a cosmic slingshot, or quantum computers unlocking shortcuts through hidden dimensions. Even multiverse travel, once pure speculation, could become a frontier if entanglement truly ties parallel realities together. The key lies in recognizing that the universe doesn't play by separate rules. It's all part of the same grand equation. Carl Sagan once marveled, "The cosmos is within us, we are made of star stuff." But today, we'd add, and quantum wonder, every atom in your body was forged in stellar furnaces, yes, but their behavior. That's dictated by quantum dances older than time, so stay curious. The next great cosmic revelation might not come from a distant telescope, but from a lab probing the subatomic deep. After all, the universe's greatest secrets don't just live out there. They're humming in the fabric of everything, including you. If this cosmic journey has left you with more questions than answers, you're not alone. That's the thrill of unraveling the universe's mysteries. Before you go, let's make sure we stay entangled. Smash that like button if your curiosity is as boundless as the quantum foam, and subscribe to keep exploring these mind-bending frontiers together. The next adventure, we're tackling time itself. What if quantum physics has already solved time travel, and we just haven't noticed yet? Here's a riddle to ponder before then. If a photon falls into a black hole, but no observer records it, does it ever really happen? Drop your wildest theories or your best guess in the comments below. Who knows, your idea might just spark the next big breakthrough. Until next time, keep looking up and looking inward. The universe's deepest secrets are hiding in plain sight.